Okay, so welcome back to the lecture series of finite volume, and what we are in the middle of discussion is the convection diffusion system, and then we started looking at the different discretization scheme for the convective flows or rather convection dominated flows, and we started with simple system, linear upwind, second order upwind, then quick from, and then we finally now doing the discussion on the high resolution scheme or higher order accurate scheme. And while in the doing show, what we are talking now to mapping between the normalized variable formulation and the TBD. So, both the system or the approach has its own criteria, boundedness criteria, which we call it the convection bounded criteria, that is CBC. So, what we have stopped in the last class is in that condition. Now, we will move forward and look at that criteria where we stopped. So, what we are doing here, we are, if you recall these things, we are trying to find out the mapping between NBF and TBD, and both of them are having different boundedness criteria. So, using those two information, so that is what we have obtained, like this is for the upwind scheme and this is how the limiter, these things are all discussed just to start with where we stop, so that we can move forward quickly from here. So, we want to find out the relationship where the R psi diagram in TBD, they look like this. So, this is the expression. Now, when you go down to normalized variable formulation and the relationship between TBD and NBF in terms of phi c tilde equals to Rf by 1 plus Rf. Now, there are limiters, and using that we tried to find out the different system. So, one case when Rf less than equals to 0. So, similar contribution, what would be the condition for the normalized variable formulation, and what we found out that this phi c tilde is less than equals to 0 or greater than 0. Then we have another relationship which is essentially the Rf 0 to positive infinity, and when that happens we find out the second relationship, and the other one which is psi Rf less than 2 lead to the tilde f less than equals to 1, and then psi Rf less than 2 Rf, and the equivalency in the NBF formulation is this. So, this is where we actually stopped in the last class. So, now if you recall and just quickly recollect from the previous discussion, what it is showing, that it is showing the one to one mapping between your NBF formulation and TBD formulation, and that is where we are in the business, and what we are trying to find out the restrictions or the boundedness criteria, and finally mapping between these two. So, what it tells you that the NBF CBC is more restrictive than the, so the this one is the TBD CBC, this criteria is more restrictive than the NBF CBC, and is the only difference between these two formulation. So, the restriction on this one is more stringent and the other way around, and the other, this one is slightly lenient. Based on this condition, what one can see that TBD CBC and the modified NBF CBC would look as we see in this particular picture. So, this side is the psi r diagram. So, this is my TBD CBC, and this side is the NBF diagram. So, also shows the NBF CBC. Now, when you look at that, so monotonicity line is reduced to the upwind and the area where it is between these two. So, that is the line which now going to be the criteria, and whereas in this case this is the line which now going to be the region of interest. Now, when you look at the TBD CBC and the NBF CBC for condition phi c tilde equals to 0, which is basically in NBF CBC, the corresponding mapping in the TBD CBC corresponds to RF equals to 0. So, that is TBD CBC criteria. So, when we see phi c tilde 0, that corresponds to RF 0. So, that also can be seen that when, so this criteria would not can be represented by this is the criteria when phi c tilde 0 corresponds to TBD RF equals to 0, and the region will be now bounded like this, and this case it will be the this triangle which will be restrictive. Now, when you talk about the second order accuracy, what we have already said that the TBD scheme to become second order accurate, it has to pass through 1 and 1, which corresponds to psi 1 equals to 1. So, this will be the equivalency that one can find out. So, equivalency is that RF equals to 1, that means phi c tilde plus 1 minus phi c tilde equals to 1, that gets you phi c tilde equals to 1 minus phi c tilde, which is phi c tilde equals to 0.5, and similarly phi f equals to phi c plus half psi 1 phi d minus phi c, which is nothing but phi c plus half phi d minus phi c, it is half phi d plus phi c. Now, if you look at psi f minus phi u is half phi d minus phi u plus phi c minus phi u. So, that gets back phi f tilde equals to 1 plus phi c tilde, which is again 0.75. So, if you now, which is the point exactly passing through 0.5 and 0.75 in NVF. So, as we have seen that the CD and second order upwind could be the, so which you can see that the second order scheme can be written as any second order scheme which can be written as weighted average of CD and SUU, which is central difference and second order upwind scheme. So, the functional relationship should lie between the functional relationship of CD and SOU, which in the TBD CBC the monotonicity region is now reduced to the upwind line and the area which is shown here, which now reduced to this. So, this is the condition when one second order scheme can be obtained. And now similar line which you get, this is your TBD CBC diagram, this is your NBF CBC diagram, and the corresponding diagram would become here in this zone. So, you see how the mapping between these two formulation can be done, and the according restriction would turn up in your discretization, and then what kind of what order of accurate scheme one has to devise, that will dictate the operational regime where it can be guaranteed that this guy would be the second order accurate. Now, this procedure can be generalized for any TBD scheme which is having an equivalent NBF scheme, or rather vice versa. So, TBD and NBF, these two formulation can be generalized for those set of schemes which has mapping between the two. So, in doing that, so let us start with the NBF framework. So, if we start with the NBF framework and how it goes. So, here the important point is that to calculate the flux at phase F. So, if you want to do that, the flux at phase F, it would be F phi c tilde phi d minus phi u plus phi u, where your phi c tilde is phi c minus phi u divided by phi d minus phi u. Again, just to give you quickly, C is the cell which is concerned, U is the upstream, D is the downstream. So, this notation is based on the local flow field direction. The direction where the flow field is acting, this will determine which cell to be U and which one is to be D. Now, when you, this is what you get for the NBF framework. Now, when you go down to TBD scheme for finding this phi f, then you get that phi f equals to phi c plus half psi r f into phi d minus phi c, where r f is the ratio between two consecutive fluxes. So, this is phi c minus phi u and phi d minus phi c. Now, if you equate these two, the TBD and NBF, equate these two, then what you get? You get phi f equals to phi c plus psi r f into phi d minus phi c equals to f tilde phi d minus phi u plus phi u. Now, that is what one can get. So, from here if you calculate back, the psi r f is psi r f into phi d minus phi c divided by phi d minus phi u, which is going to be 2 times f phi c phi d minus phi u phi d minus phi u minus 2 phi c minus phi u phi d minus phi u, which is 2 times f phi c tilde minus phi c tilde. So, the term which is sitting on the left hand side, this guy, this is the left hand side. Now, this can be now also modified, like one can write psi r f phi d minus phi c divided by phi d minus phi u, which is going to be psi r f. Now, you do some algebraic manipulation here, phi u minus phi c plus phi u. So, you add phi u and subtract the phi u, then you get this, which one can write psi r f 1 minus phi c tilde. Now, what you get is that psi r f into 1 minus phi c tilde equals to 2 times f phi c tilde phi d minus phi u minus phi c minus phi u divided by phi d minus phi u. So, that is what you get from this particular one. You just collect the terms together, which is going to give psi r f equals to 2 times f phi c tilde minus phi c tilde divided by 1 minus phi c. So, this is what you can write. Now, this one can also write phi c tilde equals to psi r f plus 2 r f 2 into 1 plus r f. It is just from here one can write. Now, the one can see by taking some example. For example, you take upwind scheme. Now, upwind scheme framework, upwind scheme in NVF framework, it provides phi f tilde is phi c tilde. Now, its TBD limiter is found like phi c tilde, where psi r f equals to 2 f phi c tilde minus phi c tilde 1 minus phi c tilde. So, that is 2 phi c tilde minus phi c tilde by 1 minus phi c tilde, which is 0. So, the upwind scheme you can find out the mapping between the TBD and the NVF. Similarly, you can get that for the downwind scheme. If you consider the downwind scheme, then what you get is also downwind scheme. The TBD limiter for that is psi r f equals to 2. So, now NVF, this will be corresponds to phi f equals to f phi c tilde, which is psi r f plus 2 r f 2 into 1 plus r f, which is nothing but 2 plus r f by 2 into 1 plus r f, which is 1. Now, if you know similarly for second order upwind scheme, if you know the NVF, if it is known, then one can find the TBD limiter, like it is phi f tilde is 3 by 2 phi c, that leads to psi r f equals to 2 times 3 by 2 phi c minus phi c 1 minus phi c, that is 2 times 0.5 times phi c tilde divided by 1 minus phi c tilde. It is nothing but phi c tilde by 1 minus phi c tilde, nothing but RF. So, similarly one can find for other scheme. So, if you know the mapping of TBD, you can find out the mapping of the NVF, or the other way around, if you find out the NVF, then you can find out the TBD. So, this is the functional relationship mapping between TBD and NVF. So, that provides a good platform for obtaining, and once you look at in the TBD diagram or psi r diagram, the restrictive limit or the boundedness, and also the NVF diagram. So, this boundedness will also map 1 to 1 accordingly, and that has a big role to play while you are devising higher resolution scheme. Now, we can extend our discussion for the higher order scheme, higher order scheme for the unstructured system. So, this is an unstructured element arrangement. So, one can see that the unstructured elements, so the cell which we are concerned of, the element C, and at the face the local velocity is in this direction. So, the D would be the downstream node and the upstream would be U, and then the other way, if the local velocity is in this direction, and then this would be the D, this is C, and then there would be a upstream node. Now, the important thing that will happen now, you need to transform them to some sort of a coordinates xi eta kind of coordinate system. Now, also what we have already seen, that the issue with the unstructured formulation. So, those things also one has to take into account. Now, the point is that, so one can very easily assume that U, this upstream node, can lie on the same line, and then one can find out a method for the higher order things. So, if you assume that this upstream node lies on the same line which connects these C and D, then what one can write, that phi D minus phi U equals to delta phi C dot D U D, which is 2 delta phi C dot D C D. So, from here one can calculate phi U equals to phi D minus 2 delta phi C dot D C D. So, you can find out that. Now, D C D is the vector between C and D, and D U D is the vector between D and virtual node U. So, as we have said that the U is constructed such that C is taken to the center of the U and D segment. So, this U is constructed in such a way that it is equidistant from the center C, or it will be on that segment. Now, with that value, with the value of phi U computed, the use of either NVF or TBD approach can be framed. So, once you get this, then use the either TBD or NVF formulation. Similarly, like that we did for the structured grid, also can be applied to this unstructured grid, and then find out the equivalent framework for the. Now, before moving that, so one important thing to talk about is the deferred corrections for high resolution scheme. So, what is that? Now, the implementation of these schemes can only be understood through some sort of an example. Now, one can take a multidimensional advection equation like del dot rho v phi equals to q with some sort of a source term. Again, this is the conservation equation. Now, what you can write, you can have a element volume for Vc for element C, and then you can apply to this divergence theorem. So, what can be depicted here, this is the C for multidimensional system. So, it is a 3D elements in an unstructured grid system. This is the face or the plane which is sort of connecting between element C and F, and this is the C element, U is the upstream of that, and the way it is that they lie on this connecting vector of C and F. So, if we take the divergence of these, I mean basically, and after that surface integral, this equation turns out to be NBC rho v phi at F SF equals to QC BC. So, that is our standard equations with source term. Now, mass flow rate at the face m dot F is given as rho v F dot SF, and then one can write the equation NBC m dot F phi F QC BC. So, that is the semi discretized form. Now, the point is that the value of phi F is obtained by using some sort of an advection scheme discretization that we have discussed already, and then the whole system will completely becomes an discretized system or the algebraic system in a form AC phi C plus capital F NBC AF phi F equals to BC. Since it has some source term, the BC is not going to be 0 anymore. Now, again the difficulty lies in the instability which arises due to calculation of phi F in terms of nodal value, because this is a unstructured grid system. So, when one try to find out this phi F using the nodal value, that is where some sort of an difficulties one can face. Now, what kind of difficulties one can face? So, let us say when you try to explicitly derive phi F using the neighboring values and use the TBD framework. So, if that is the case, then my m dot F phi F, one can write that phi C plus half xi, which is phi C minus phi u by phi F minus phi u, which is nothing but your, this is my RF into phi F minus phi C multiplied with m dot F 0 minus similarly phi F plus half psi, there it would be phi F minus phi d d by F phi C minus phi F. This is again the RF minus, this is the RF plus multiplied with phi C minus phi F multiplied with minus m dot F 0, the magnitude. From there you can get phi c plus half psi r f plus phi f minus phi c multiplied with m dot f 0 minus phi f plus half psi r f minus multiplied with phi c minus phi f minus m dot f 0. So, now if you substitute this one, this case m dot f phi f, this guy, what we have got into this equation. So, we will stop here and we will continue the discussion in the next lecture. Thank you.